That's what this section is about, arc length. I'll just leave that there. So how do we go about this? Well, we've got this awesome tool, right, that allows us to add things up, the integral. So I just got to figure out what I want to add up. So quick recall here. This is 7.4 arc length. We call it the arc length, all right? Recall that if y is some function of x, right? If y is some function of x, I can graph this. Now let's say I start here at A and I end here at B. And I want to know how long this is, right? If you were to take that off the page and straighten it out, what's the length? Well, what if we zoom in, okay? Let's take like a really small little piece of this function. Really small. So I'm going to take this infinitesimally small piece and I'm going to zoom in on it, all right? So we are now zoomed into this infinitesimal little piece of this function. And when I look at it through my magnifying glass, it looks like that, all right? And so I'm going to imagine this point right here and this point right here. I'm going to imagine creating a right triangle like this. Now this is curved, right? This is curved. My triangle, if I complete my triangle is definitely not curved, right? It's a straight line here. But this red line right here, the hypotenuse of this triangle, should be really close to the length of that curve, right? And if I zoom in more and more and more and more, then these should essentially come together, shouldn't they? The curve should have less error. I should have less gap in here the more I zoom in. This is back like when we were doing the areas under curves. I said, let's cut it with rectangles, right? Okay, if we do 3 rectangles, we're going to be off. We're going to have a lot of error. But if we did 10 rectangles, it's better, right? 100 rectangles, it's better. If we let the number of rectangles go to infinity, right, then we get the true area. Well, that's exactly what I'm doing here. I'm saying if I approximate the length of one little piece with this hypotenuse, I'll have some error. But if I take a limit that lets me zoom in, zoom in, zoom in, zoom in, my error essentially goes to nothing and I get the true length. Do you buy that? I mean, that's what the limit allows us to do. So that means all I need to do is figure out a formula for that length right there, right? Just a formula for this length from here to here. I'll call that little l. Little l right there is that distance from here to here. Well, here's what I know though. If I were to look at that little infinitesimal slice, the left edge, this left corner right here, would be some point on the x-axis, right? And the right edge, if you come down, would be some point on the x-axis. And that would be this infinitesimally thin little piece, right? What have we been calling that? Dx, right? So we know that this side is dx, right? And then the height, okay, this side right here would be this, which would be dy, how much y is changing. So we'll call that let's just call it dy. Did y'all buy that so far? Okay, so the length then, I could say this, dx squared plus dy squared must be L squared. That's just Pythagorean, right? A squared plus b squared is c squared. And I want to add up, I want to get the L by itself, so I'm going to take the square root over here of dx squared plus dy squared equals L. Do I have a formula for one of these? Do I have a formula for L? Yeah? Can I add it up now? Yes, right? I can just add those up. So if I want to add those up, I'm going to do an integral that's going to start at A and end at B. And what is it that I'm adding up? The L's, right? Which is the square root of dx squared plus dy squared. That's it, right? That's what I'm going to add up. And we run into a problem. This looks different than anything we've had before, right? And everything we've had before, haven't we always had like dx on the outside or something like that? Here I got a dx squared and a dy squared. What the hell is that? All underneath the root. This is looking kind of weird, right? So now I'm going to ask you to remember something. Leave that there. If y is some function of x, right? So that's what this was, right? This was our function of x here. If y is some function of x, then if I take the derivative of y with respect to x, that's the definition of what it means to be f prime, right? F prime is exactly the same as dy dx, yes? Now I'm going to multiply both sides here by the differential dx. So I have a formula for dy. It's f prime of x times dx, right? So I'm multiplying both sides by dx here. This is what dy is. So I'm going to come back over to this formula here, and I'm going to replace dy with f prime of x times dx. And I think I'll do that. I want to leave this, I want to leave all that there. I'll put it right here. No, I'll put it right here. So I'm trying to do this integral, right, from a to b of the square root of dx squared plus dy squared. But I just found a formula to replace the dy. So this is dx squared plus, now I have f prime of x times dx, but that whole quantity squared, right? That's what dy is. And when you square two things that are multiplied, you square each one, don't you? So if I square each one there, we get integral a to b, we get square root of dx squared plus f prime of x, whatever the derivative is, take that and square it, but then times the dx squared. So I just squared each one, right? Squared each of these. What do those both have in common? Dx squared. If they both have dx squared, I can factor it out, right? And then because it's squared, I can take the square root. And it can come outside of the root as a what? Just dx. Right? I'm going integral a to b. I'm factoring out the dx squared from here. So I'm factoring out dx squared. I get 1 plus f prime of x. I'll put it in brackets because that's what the book does, squared. Okay, so I took dx squared away from here. It leaves me with a 1. Take dx squared away from that, leaves me with f prime of x squared. Now this is multiplication. I can do the square root of each one, and I get my final formula, which is this. That the length, the total length of the entire curve will be the integral from a to b of the square root of 1 plus whatever the derivative of f is, that squared times dx. So I brought the dx out in front of the root, but then I moved it to the back. That's the formula for the length of a curve. If you want to know how long a curve is, then you've got to be able to evaluate this integral. Questions? Yes? Okay. From here I did the square root of dx squared times the square root of 1 plus. So I just broke it into two roots because there was multiplication. Got it? So split this up into two roots. That right there is just dx, and I just moved it to the back. All right. Good? All right, so let's do an example. How long is that curve? That one right there. That's the sine curve. Find the length of y equals sine x on the interval 0 to 2 pi. Haven't you ever wondered how long the sine curve is? Yeah, of course. Probably kept you up late at night, hasn't it? How long is that curve? All right, well, I just need that formula, right? So in that formula, I need to know what the derivative is. So let me figure out what the derivative is. The derivative of this function is cosine. And we're like, yes, right? Easy derivative. Okay, then I need to square it, right? So if I need to square that, I'm just doing work right now, just kind of like groundwork to get myself ready. If I square that, well, that's just cosine squared x, right? No big deal. And then I need to do plus 1 and stick it under the root. I think I'm ready to put the integral together here. So this is going to be, the length will be the integral from 0 to 2 pi, because that's what I was given, the square root of 1 plus cosine squared x dx. That's it. That's the length of that curve, if I can figure out what this is. Seem fair? Now, I made up this example because that's what I had on the board. And you can see the formula being used pretty easily there, right? The derivative, square it, add 1, put it under a root, you're in business. Here's the problem. That integral is going to be impossible for us to do. Unfortunately, we don't have anything to do that. So right now, if I ask the computer to give me the antiderivative of the square root of 1 plus the cosine of x function squared with respect to x. With respect to x. That's the integral, right? Just finding the antiderivative. Let's see what Wolfram alpha does here. Oh, yep, it gave me the root 2 e of x. What the heck is this? Oh, it's the elliptic integral of the second kind with the parameter m. What the hell, right? So this basically means, hey, we can't do that by hand, all right? Now, if I change the problem, okay, if I change it and I do a definite integral on Wolfram alpha, which means I go from 0 to 2 pi, and then I do that thing, square root of 1 plus cosine of x squared, and ask it for that answer, it's going to have no problem. It's going to give me a numerical answer, 7.64. 7.6404. It gave me a numerical answer, right? Our calculator, our computers are always going to be able to give us numerical answers because the computer is using, does anyone remember what I told you? Series. It's using series. And so we haven't talked about series yet, but I can show you how that we get that answer. When we get into chapter 8, I can show you how we could get this answer. But right now, as is, the very simple sine curve, right? Very simple sine curve, we can't find the length of it by hand because we can't do that antiderivative. Do y'all see there's nothing we can do here? Basic u sub, right? Go back to the beginning of integration. Basic u sub. Do you see something in its derivative? No. Oh, if this was a minus, things would be good, wouldn't it? It's not a minus, though. So you can't do a Pythagorean identity there. You can't do trig sub. Even though this kind of looks like a trig sub, you can't, because even if you call cosine of x u and make it kind of look like trig sub, you don't have du. You don't have its derivative anywhere. So do you all believe me when I tell you that we can't do that? Okay, so we're just going to have to leave it alone. All right, well, let's do one we can do then, yeah? So how about this? Find, I don't know if I want to push y'all here yet, but yeah, let's go for it. Find, or I'm not going to say find, I'm going to say prove the circumference of a circle is 2 pi r. I want us to prove that the circumference of a circle is 2 pi times the radius. A couple of classes ago, we proved that the area of a circle was pi r squared, right? Do you remember how we did that? Go back in your notes. What we did in that class was we took the circle in the first quadrant only, and we wrapped it around the x-axis, right? And we found the volume of it that way, and then we doubled that answer. Here, if I want to prove that the circumference of a circle is 2 pi r, then can't I just find the length of that piece and multiply times 4? Yes? So what is this? What is this curve? We did it in our notes. We solved that, and we wrote it as a function of x. Do you have it written down anywhere? X squared plus y squared was r squared. So this was r. But then we solved for y. And when we solved for y, we got y was r squared minus x squared underneath the root. Do I need to go through that again? You okay with that? This circle of radius r has as its oh my gosh, has as an equation x squared plus y squared is r squared. Solve that for y, you get this, right? Okay, that is our function of x. R here is a constant. R is a constant. I'm going to use this formula now. So I need the derivative. I need to square the derivative. I need to add 1 to the derivative, and I need to take the square root, right? That's what I need. So let's do some scratch work here. What is the derivative of that function? So what if we're saying f of x is the original curve, square root of r squared minus x squared. What is the derivative of that? Chain rule, right? Chain rule. Derivative of square root of anything is 1 over 2 roots of whatever was there, right? Times derivative of what's inside. Negative 2x, that's it, right? The r squared, when you take its derivative, it goes to 0. So derivative, that's that. That's your derivative, right? The 2's go away. So this is really just negative x over the square root of r squared minus x squared. Yes? Okay. We need to square that now, right? In the formula, we need to square it. Let's square that over here. If we take that derivative and square it, we square the top. Hey, that's good. The negative goes away. We get x squared. And shit, look at that. If we square the bottom, the root goes away. And we just get r squared minus x squared. This going okay? I think I'm ready to go to the formula. Maybe leave this for a minute here. The length should be the integral, okay, a to b. Where are we going to go from? Where are we integrating from? 0 to r, right, to the radius, 0 to r. So go 0 to r, square root of 1 plus, that's the formula, and then the derivative squared, which is x squared over r squared minus x squared dx. There's our formula with the derivative squared plugged in, right? I just did all that over there so I didn't have to do it in the integral. Just got all that kind of figured out first. Now, unfortunately for this looks bad. This looks bad. It's not bad, though, okay? Just get a common denominator between these two. So if you get a common denominator between those, I don't need this anymore. If I get a common denominator between those, it becomes integral 0 to r square root of, what do we get on top? Just r squared, right? If you get your common denominator, multiply top and bottom by r squared minus x squared. When you add these two together, the x squareds cancel. And all you get is r squared on top. And on the bottom, you have the common denominator. And then that, 0 to r, I can do the root on the top and bottom separately. So if I take the square root of the top, what's the square root of r squared? R, right? And r is a constant. So I could actually take, well, yeah, I'm going to take it now. I'm going to take the r that was on top, and I'm going to take it out. Okay, so I did the square root of the top, which is r, I pulled that r out of the integral. On the bottom, I still have square root of r squared minus x squared dx. Questions on that step? Now just imagine that r was a number, okay? R is, let's say, 4. Then this would be 16 minus x squared, right? Underneath the square root. How would you do that? Trig sub, right? That's a trig sub problem, isn't it? Trig sub. Now I'm not going to go through the trig sub, right? It's a pretty straightforward trig sub, this one, all right? So can I just go the next step? If you did trig sub at this point? If you did trig sub, here's what you would get. R times the antiderivative of that will be arc sine of x over r. That's what happens with trig sub. You get that right there. In fact, this is a formula on your sheets. We have a formula for 1 over the square root of a squared minus x squared. That's a formula on your sheets. Are you looking for it? You see, I'm curious to know which one it is. 16, formula 16. This is number 16 on your formula sheets. But we're using r instead of a. Okay, that's the antiderivative, right? Evaluation bar. This is our fundamental theorem of calculus, right? 0 to r. Okay, we're going to plug in. We're going to get two things here. All right, when we plug in r, we get r times sine inverse of r divided by r is 1. And then over here we get r sine inverse of 0 divided by r, which is 0. And now you're back in pre-cal, and you're saying, what is sine inverse of 1? So that means you're saying, on the unit circle, where's the y-coordinate 1? Pi over 2. So this is r times pi over 2 minus, and then here this is saying, okay, on the unit circle, where's your y-coordinate 0? At 0. So this is 0, which means this is 0. So your answer to all of this is r times pi over 2. You could write that as 1/2 pi r. Half of pi r is the length of that curve. Right? And then multiply times 4, and you get 2 pi r. And we've verified. Pretty nice, huh? You need trig sub. You have to have trig sub to show that the, to show that the circumference of a circle is 2 pi r, you need trig sub to do it. And you need the formula for arc length. All right. So here's what I'm going to say about this. The problems that you're going to have for the homework on this, the algebra is really going to be the part that's tricky. So just see how it goes. You have my homework solution videos to guide you. See how those problems go. They're going to be harder than what I just did. I'm just warning you about that. All right, 7.5. Surface area. We're almost done. All right, the idea here is pretty much the same thing that we just did. Well, I strike that, okay? It's nothing like we just did. What we've been doing with regions is wrapping them around and getting volumes, right? Volumes, that's what we kind of finished up today. But those solids that we were making, don't they have surface areas as well? So imagine that you take a curve, let's say some curve like this. Let's just call that f of x, all right? Let's say you started at A and you ended at B. And you're going to take just that curve and wrap it around the x-axis. Let's start with that x-axis. You wrap it around the x-axis, all right? Don't create a solid. Just the curve itself goes around. And it would create this like shell shape, right? It would be hollow on the inside. There it is right there. Yeah, there it is right there. There's a little curve, and you're just going to wrap it around the x-axis, and you create this hollowed out shell, right? And what the question here is what's the area? What's the surface area of that shape, right? What's surface area? So if we wrap this around the x-axis, go around, we're going to create this shape that looks, I don't know, something like this. All right. And this thing has an area. And the question is, what is that area? So the way we're going to do it, believe it or not, is we're going to use the idea we just talked about with arc length. So imagine that you take a zoom in here, okay? You're going to zoom into this little infinitesimal piece, and you're going to take that little piece right there, and you're going to wrap just that around the x-axis, just that piece, right? Imagine that goes around the x-axis. You're going to create this shape. It's not a washer, it's a rubber band. Do y'all see it? It's a rubber band. Because only this top edge went around. We didn't take a rectangle and wrap a rectangle around and create this washer or disc. We just took this edge and wrapped it around and created this rubber band sitting in space. And what I'd like to know is, what is the area of that rubber band? What's the area of it? So I come in here and I snip it with my scissors and just cut it. And I lay it open. And when I lay this open, I've got my little rubber band here, right? It's my rubber band laid open. How long's the rubber band? Well, it would be the circumference of this thing, right? It'd be the circumference of the rubber band. And the circumference is 2 pi r, right? What's the radius for us? What's the distance from the center to that top edge? It's not r, it's what? It's f of x, right? It's that distance from here to here. That's our radius, which is the function itself. So the length of this should be 2 pi times f of x. So that's our circumference formula, 2 pi r. But our radius is that distance from the x-axis up there. Got it? How thick is it? Yes. So I know you want to say dx. I, as a student, wanted to say dx myself. But we have a better, more accurate number. Because remember, we took this and we cut it, right? Like we cut this little piece out. And so isn't that really, isn't that width here? Isn't it actually how long that little piece was? Isn't it the length of that arc? Right? If you zoom in on that, right? You have your curve cutting through here. We cut this, right, to make our rubber band. We're going to use this as our this is our length. Okay, that's how long this is. And so this d, what you want to be dx, is actually the length of the arc. And we have a formula for the length of the arc. We just created that. It was square root of 1 plus the derivative, that thing, squared dx. I know that sucks, but that's what it is. So we know how tall this is, and we know how wide it is. The width is the arc length, the arc length of that little piece, and then the length here is the circumference of the rubber band, which is 2 pi times f of x. And we want to add all those up, so we want to throw them into an integral. Right? Add them up, so you're just multiplying those two together, right? If you multiply those two together, the 2 pi can come out, can't it? We're still going to go from a to b. And then it's going to be the f of x, right? And then the square root of times this, square root of 1 plus f prime of x, that thing squared, dx. That's our formula. That's very similar to the arc length formula, right? It's almost the same formula, with one exception. Well, two. You have 2 pi on the outside, and you have f of x in front of that. If you take that away and take that away, you're talking about the arc length. You put this here and this here, and now you're talking about the surface area of the whole thing. All right, I've got 3-4 minutes, so you ready? That's our formula. Prove the area is 4 pi r squared. So if you take a sphere, three-dimensional sphere, okay, a ball, the area of it is 4 pi r squared. Prove it. Okay? So what am I going to do? Anyone know what I'm about to do? Yeah, I'm going to do the same exact thing we were just doing, right? Like, take that circle in that top corner, right? We're going to wrap this around the x-axis, but this time we're getting what? Surface area, not volume, right? So if I wrap this around the x-axis, let's see what happens. I know I'm moving fast, but this is the equation y equals square root of r squared minus x squared, right? If I wrap this around the x-axis and find that surface area, then all I have to do is double it, and it would give you the other side, right? Now we give you this. Following? Okay, so let's see. We have to set all this up, right? We have to do all this. Well, what's the difference? Didn't we already do this? Didn't we already do this? We did all that already, didn't we? The only difference between the integral I'm about to put up here and the integral we just did a second ago is that we need to add an f of x and a 2 pi to it. So can I do that? So let me do it. I'm going to do 2 pi. We're going to go integral from 0 to r. What was our integral? What was this? What was this part in blue for us? 1 over, right? 1 over the square root of r squared minus x squared, right? And then we had an r on top, didn't we? Yes. And we had pulled that r out. I'm not going to pull the r out this time. I'm going to leave the r here. Square root of r squared minus x squared. And then dx. That's what the old integral was before. If these two weren't here, that's what we had, right? Okay, but we need to add to that the 2 pi, which we've done. And we need to add f of x right here. What's f of x? It's this, right? It's this. Yeah. And do you see what's going to happen? This is f of x. What's going to happen? Holy shit. That is a constant. That's a constant, right? I mean, that's just r inside. So this is 2 pi. Shit, I'll even pull the r out. Integral 0 to r of 1 dx. Look, these went away. And all I had was the r here, which I pulled out. And now what's the antiderivative of 1 with respect to x? X. So this is just 2 pi r times x, but evaluate